You think motion is real. Of course you do. You see things move all the time. Cars drive past, birds fly overhead. The earth spins beneath your feet. You yourself walk from room to room, your body traveling through space from here to there. Motion seems like the most obvious, undeniable fact about reality. Things move. They go from one place to another. They have positions at different times. What could be more straightforward than that? But here's the problem. When you actually try to say what motion is, when you try to define it precisely, when you ask the hard questions about what's really happening when something moves, you discover something disturbing. Motion, as you imagine it, doesn't exist. Not in the way you think it does. The smooth, continuous journey you picture in your mind, the object gliding from point A to point B, that's not what's happening. That's not what the universe does. What you call motion is something much stranger, something that breaks apart when you look too closely. Something that reveals the entire foundation of your everyday experience to be built on assumptions that simply aren't true. Richard Feynman understood this better than almost anyone. He had a way of taking the things everyone thought they understood and showing them the hidden machinery underneath, the places where common sense broke down completely. And motion was one of his favorite examples because it seems so simple, so obvious. Right up until the moment you realize you've been fooled your entire life by the way your brain processes visual information. Let me show you what he would show you. Let's start with something everyone knows. You throw a ball, it leaves your hand, travels through the air, and lands on the ground. Simple. The ball moved. It went from here to there. You saw it happen. You can describe it. You can predict where it will land. Motion seems perfectly well defined. Now let me ask you a question that's going to make you uncomfortable. Where was the ball 1 second after you threw it? You can answer that. You can calculate it. You know its initial velocity. You know gravity is pulling it down. You can figure out exactly where it should be. Fine. Now tell me where the ball was at exactly half a second. You can calculate that too. Now tell me where it was at 1/4 of a second, 1/8, 1/16. Keep going. Where was the ball at exactly 1/millionth of a second after you threw it? You're starting to see the problem. To describe the motion, to say the ball traveled from here to there, you need to know where it was at every single moment in time. But time doesn't come in chunks. Time is continuous. Between any two moments, no matter how close together, there are infinite other moments. So, for the ball to travel from your hand to the ground, it has to occupy an infinite number of positions. Not just a lot of positions, infinite positions. This is Zeno's paradox, and it's been bothering people for 2,500 years. The Greek philosopher Zeno pointed out that to get anywhere, you first have to get halfway there. But to get halfway, you first have to get 1/4 of the way. And to get 1/4, you first have to get 1/8, and so on forever. You have to complete an infinite number of steps. But how can you complete an infinite number of anything? Infinity never ends. So motion, Zeno argued, is impossible. It's an illusion. Most people dismiss this as a word game, a philosophical trick. Obviously things move, they say. Obviously we get from one place to another. Just look around. But Feynman would tell you that dismissing Zeno is a mistake. Not because Zeno was right, but because Zeno was asking exactly the right question. He was asking what actually happens when something moves, not what it looks like to your eyes. And once you start asking that question seriously, Once you demand a real answer, not just a description of appearances, everything you thought you knew starts to crumble. Here's what your brain does when you watch something move. It takes a series of snapshots, visual frames captured by your retina, and stitches them together into a continuous story. The ball was here, now it's here, now it's here. Your brain fills in the gaps. It creates a smooth narrative of continuous motion. You don't see the individual frames, you see the movie. And that movie, that smooth, continuous glide from one position to another, that feels real to you. That feels like motion. But that's not what's happening in the physical world. That's just your brain's reconstruction. Your visual system evolved to track predators and catch prey, not to reveal the fundamental nature of reality. It evolved to give you useful approximations, not perfect truth. And the approximation it gives you is that things move continuously through space. The question is, do they? Is motion actually continuous, or is that just how your brain interprets the data? Let's think about what continuous motion would mean. It would mean that at every single instant of time, the ball has a precise position and a precise velocity. Position and velocity. Where it is and how fast it's going. That seems reasonable. At this instant, the ball is at position X with velocity v. 1 instant later, it's at position X plus a tiny bit with velocity v plus or minus a tiny change. String all those instants together and you get continuous motion. But here's where Feynman would grab you by the shoulders and make you think harder. What does it mean to have a velocity at a single instant? Velocity is distance divided by time, meters per second. To have a velocity, you need to travel some distance in some amount of time. But an instant has no duration, zero time. So how far does the ball travel in zero time? Zero distance. 0 divided by 0. That's not a number, that's undefined. You might say, well, velocity at an instant is the limit as the time interval approaches 0. That's calculus. That's what Newton invented to solve exactly this problem. And you're right. Calculus works beautifully for predicting where things will be. But here's the thing Feynman would point out. Calculus is a mathematical tool, a computational technique. It's not a description of physical reality. When you calculate a velocity using calculus, you're taking an idealized mathematical limit that never actually occurs in nature. You're imagining what would happen if you could make the time interval infinitely small. But you can't actually do that. Time doesn't work that way. So the smooth, continuous motion that calculus describes, that's a mathematical model. It's incredibly useful. It makes predictions that work. But is it real? Is that what the ball is actually doing? Or is it just a convenient fiction that matches our observations? Now you might be getting frustrated. You might be thinking, this is just philosophy, just words. Who cares if motion is real or just a model? The ball lands where we predict it will land. That's all that matters. But Feynman cared deeply about this distinction because he knew something most people don't. When you look at the universe at small scales, at the scale of atoms and electrons, motion stops making sense, not just philosophically, physically. The entire concept breaks down. Here's what happens when you try to pin down the motion of an electron. You want to know where it is and how fast it's going, its position and velocity. That seems like a reasonable thing to ask. But nature says no, not approximately no, fundamentally, absolutely no. This is the Heisenberg uncertainty principle, and it's not about measurement error or technological limitations. It's about reality itself. The more precisely you know an electron's position, the less precisely you can know its velocity. The more precisely you know its velocity, the less precisely you can know its position. There is an unavoidable trade-off built into the structure of quantum mechanics. You cannot simultaneously know both with perfect precision. It's not that the electron has a precise position and velocity, and we just can't measure them. It's that the electron does not have a precise position and velocity at the same time. Those quantities do not simultaneously exist. Think about what that means for motion. Motion requires knowing where something is and where it's going. But for an electron, you can't know both. So what is the electron doing? Is it moving? The question itself becomes meaningless. You can't describe continuous motion for something that doesn't have a well-defined position and velocity at the same time. Feynman spent much of his career working on this problem, developing a completely different way to think about what particles do. He created what's called the path integral formulation of quantum mechanics, and the picture it gives you of reality is absolutely bizarre. Here's how Feynman would describe it. Imagine you want to know the probability that an electron gets from point A to point B. In classical physics, you'd say the electron follows a specific path, a trajectory. You calculate that path using Newton's laws or calculus, and that path is the motion of the electron. But Feynman showed that's not what happens. The electron doesn't follow a single path. It follows every possible path simultaneously. The straight path, the curved paths, the wildly looping paths, the paths that go backward in time and then forward again. Every single path you can imagine, and infinite paths you can't imagine. All of them at once. Each path contributes to the final probability with a certain phase, a certain quantum amplitude. And when you add up all the contributions from all the infinite paths, most of them cancel out. The wild paths cancel with other wild paths. What's left is a peak of probability around the classical path, the path Newton would have predicted. That's why large objects seem to follow definite trajectories. It's not that they actually do. It's that all the other possibilities cancel out, leaving only the classical-looking result. But for an electron, for a small quantum particle, those other paths matter. They don't completely cancel. The electron genuinely explores multiple paths at once. It interferes with itself. It acts like a wave spread out over space, not like a particle moving along a line. So when you ask, where is the electron and how fast is it moving? The question contains a false assumption. It assumes the electron is a tiny ball with a definite position, traveling along a definite path. But that's not what an electron is. An electron is a quantum probability distribution, a cloud of possible positions with different likelihoods. And that cloud evolves over time in a way that doesn't correspond to any single smooth path through space. Motion, as you imagine it, does not exist at the quantum level. There are no trajectories. There are no smooth, continuous journeys. There is only the mathematics of probability amplitudes, evolving over time. And when you measure the electron, the cloud collapses to a single outcome, giving you the illusion of a particle with a definite position. Now you might be thinking, okay, quantum mechanics is weird, but we're not electrons. We're macroscopic objects made of trillions of atoms. Surely motion is real for us, even if it's weird for individual particles. But here's the thing Feynman would make you confront. You are made of electrons. You are made of quarks and photons and quantum fields. The ball you throw is made of atoms that are themselves quantum mechanical. So if motion isn't real at the fundamental level, if particles don't actually move along smooth paths, then how can the motion of the ball be real? The answer is that the motion you see is an emergent property, a large-scale average that hides the underlying quantum chaos. When you have trillions of atoms all doing their quantum probability distribution thing, and you average over all of them, the quantum weirdness mostly cancels out. What's left looks like classical motion, looks like smooth, continuous trajectories. But that's an approximation, a useful simplification of something far more complex. Let me make this concrete with one of Feynman's favorite examples. Imagine you're watching a drop of ink spread out in a glass of water. The ink starts as a concentrated blob, then it diffuses, spreading out until the whole glass is faintly tinted. You might describe this by saying the ink molecules are moving through the water, bouncing around randomly, gradually spreading out. But Feynman would tell you to look closer. What's actually happening? The ink molecules are not little balls rolling around. They're quantum probability distributions interacting with the quantum probability distributions of water molecules through electromagnetic forces. The whole thing is a staggeringly complex quantum many-body problem. No individual molecule has a well-defined trajectory. They're all clouds of probability interfering with each other. But when you zoom out, when you look at millions of molecules at once, you see diffusion. You see a smooth, spreading pattern that obeys simple mathematical laws. The motion of the ink appears smooth and continuous because you're averaging over countless quantum interactions. The smoothness is an illusion created by scale. This brings us to a deeper question that Feynman loved to explore. What does it mean for something to be real? You see motion, you can measure it, you can predict it. You can use it to build machines and launch rockets. So in what sense is it not real? Feynman's answer would be that motion is real as a description, as a model, as a predictive tool. But it's not real in the sense of being a fundamental feature of the universe. The universe doesn't have motion as a basic ingredient. The universe has quantum fields and probability amplitudes and symmetries and conservation laws. When you put all of those together and look at them from a macroscopic perspective, you get something that looks like motion. But motion itself is not in the recipe. It's an emergent pattern, a shadow cast by deeper processes. Think about a movie. When you watch a film, you see people moving, cars driving, objects falling. But what's really on the film? Still images, individual frames, each one completely static. Motion appears when you play those frames in sequence fast enough that your brain stitches them together. The motion is not on the film. The motion is created by the projection process and your visual system. Reality might be similar. The universe might be a series of static configurations, snapshots of quantum states, each one containing no motion whatsoever. And what you experience as motion is your brain's interpretation of how those configurations change from one moment to the next. The motion is not in the configurations. It's in the transition between them, and even then, it's more accurate to say it's in your perception of that transition. Now let's go even deeper, because Feynman didn't stop at quantum mechanics. He was also fascinated by relativity, by Einstein's realization that space and time are not separate. And when you combine quantum mechanics with relativity, the idea of motion becomes even more problematic. In relativity, time is not a universal background against which things move. Time is a dimension, like space. The universe is a four-dimensional structure called space-time, a static block where every event that ever happens is laid out like cities on a map. Your entire life, from birth to death, exists as a continuous thread through that block. You don't move through space-time. You are a four-dimensional object, a world line, extended in time just as you're extended in space. From this perspective, motion is just a way of talking about how your world line is oriented in space-time. When we say you're moving through space, what we mean is that your world line is tilted in the time direction. You have a larger temporal component than spatial component. But you're not actually going anywhere. You're just existing as a static structure in four-dimensional space-time. This view is called the block universe, or eternalism, and it's the natural interpretation of relativity. If the universe is a four-dimensional block, then the past, present, and future all exist equally. There is no flow of time, no motion from past to future. There is only the static geometry of space-time, and your perception of motion is just the way your consciousness experiences its path through that static structure. Feynman was deeply aware of this tension. He worked on quantum electrodynamics, the theory that combines quantum mechanics and special relativity. And in that theory, particles don't move in any conventional sense. They exist as excitations in quantum fields. An electron is not a little ball moving through space. It's a ripple in the electron field, a pattern of energy and probability that shifts and changes according to quantum laws. When we say an electron moves from point A to point B, what we really mean is that the electron field had a high amplitude at point A at one time and a high amplitude at point B at a later time. But the field itself is everywhere all the time. The particle is just a temporary concentration, a wave packet that appears to move, but is really just a pattern of field oscillations propagating through space. And even that description is too classical, too committed to the idea of definite positions at definite times. In the full quantum field theory, you don't even have that. You have quantum operators acting on abstract state vectors in Hilbert space. And the whole question of where something is, or how it's moving, becomes a question of what observable you choose to measure. So let's take stock. At the classical level, motion seems obvious, but it's actually a mathematical idealization that requires infinitely many positions and velocities that can't be precisely defined. At the quantum level, motion breaks down completely because particles don't have simultaneous position and velocity. At the relativistic level, motion disappears into the static geometry of space-time. And at the quantum field theory level, particles themselves are just temporary patterns in underlying fields. At every layer, when you dig deeper, motion becomes less and less like the smooth, continuous journey you imagine. It becomes more and more like a useful approximation, a shorthand for something far stranger. But here's the beautiful thing that Feynman would want you to understand. Just because motion isn't fundamental doesn't mean it's useless or wrong. The opposite. Motion is one of the most powerful concepts in physics, precisely because it's a high-level description that captures the essential behavior of complex underlying systems. When you throw a ball, you don't need to solve the Schrödinger equation for every atom in the ball. You don't need to track every quantum probability amplitude. You just use Newton's laws. You treat the ball as a classical object with a position and velocity, and you calculate its parabolic trajectory. And it works. It works brilliantly. That's not despite the fact that motion is emergent. It's because motion is emergent. Emergent properties are not less real in practical terms. They're more real because they're the level at which we can actually understand and manipulate the world. Water is wet, even though individual water molecules are not wet. Temperature is meaningful, even though it's just the average kinetic energy of molecules. Motion is useful, even though it's not a fundamental feature of quantum fields. Feynman understood this better than almost anyone. He could work at the deepest levels of quantum field theory, calculating Feynman diagrams and renormalizing infinities, and then turn around and explain why a ball curves when you throw it with spin. He moved fluidly between levels of description, using whatever conceptual tools were most appropriate for the problem at hand. And he never confused the map with the territory. He never mistook the mathematical model for physical reality. Here's one of the most important lessons Feynman tried to teach. Physics is not about saying what things are. Physics is about saying what things do. We don't know what an electron is in some deep ontological sense. We know how it behaves. We know how it responds to forces, how it interacts with other particles, how it creates observable effects. That's what we can measure. That's what we can predict. And that's enough. When we say an electron moves, we're really saying that if we measure its position at different times, we'll get different results in a predictable pattern. The motion is shorthand for that pattern of measurement results. It's a convenient way to organize our predictions. But the motion itself, the smooth, continuous path we imagine in our heads, that's our mental model, not nature's reality. This is why Feynman was always suspicious of explanations that relied too heavily on visualizations or analogies. He knew that our mental images are built from everyday experience, and everyday experience is macroscopic and classical. When you try to visualize quantum mechanics or relativity using mental images built for a world of balls and springs, you inevitably get confused because those images don't apply. The right way to understand these things, Feynman would say, is through the mathematics. Not because math is more real, but because math is more flexible. Math can describe relationships and patterns that don't correspond to any visual image. And when you let go of the need to picture things, when you accept that the equations are the description and the pictures are just crutches, you can actually understand what's going on. But most people can't do that. Most people need the pictures, need the stories, need the smooth, continuous motion to make sense of the world. And that's fine. That's how we're built. Feynman never faulted people for thinking in terms of motion. He just wanted them to know that motion is a useful fiction, a story we tell ourselves that approximately matches reality at human scales, but breaks down when we look too closely. Now let's bring this all back to where we started. You throw a ball. It travels through the air and lands on the ground. What really happened? At the deepest level, quantum fields fluctuated. The electromagnetic field, the electron field, the quark fields, all of them shifted and evolved according to the Schrödinger equation, or, more accurately, according to the path integral over all possible field configurations. Trillions of atoms worth of quantum probability amplitudes propagated through space-time, interfering with each other in fantastically complex ways. The atoms in your hand pushed on the atoms in the ball via electromagnetic repulsion. Energy transferred from the chemical bonds in your muscles to the kinetic energy of the ball's atoms. The ball separated from your hand and entered a different region of the gravitational field. The atoms in the ball interacted with the atoms in the air, exchanging momentum in countless collisions. Gravitational attraction between the ball and the Earth curved the space-time geometry infinitesimally, and the ball followed a geodesic through that curved space-time. Eventually, the ball's atoms collided with the atoms in the ground. More electromagnetic repulsion, more energy transfer, more quantum field interactions. The ball came to rest. At no point in that story did the ball move along a smooth, continuous path. At no point did it have a precise position and velocity at the same instant. What happened was a staggeringly complex evolution of quantum states, and when you average over all of it, when you zoom out to macroscopic scales, you see something that looks like motion. But the motion is an emergent description, high-level summary of low-level quantum chaos. Does that mean motion is an illusion? Not exactly. It means motion is a model, a way of organizing our observations, a predictive framework that works at certain scales. It's real in the sense that it makes accurate predictions. It's not real in the sense that it's not part of the fundamental furniture of the universe. Feynman would probably put it this way: asking whether motion is real is asking the wrong question. The right question is, does the concept of motion help us understand and predict the behavior of physical systems? And the answer is yes, absolutely, at appropriate scales and for appropriate purposes. But when you push the concept too hard, when you demand that it work at all scales and answer all questions, it breaks. It fails at the quantum level, because particles don't have trajectories. It fails at the relativistic level, because time is not a universal background. It fails philosophically, because continuous motion requires completing infinite tasks. The lesson here is not that physics has failed to explain motion. The lesson is that motion, as you intuitively understand it, was never the right concept in the first place. It was always an approximation, a useful simplification of something more complex. And the genius of modern physics is that it found better concepts, deeper concepts, quantum fields and symmetries and conservation laws that actually do describe what's happening at the fundamental level. Those concepts are harder to visualize. They don't match your everyday experience. They require mathematics to express properly. But they work. They make predictions that match experiment to extraordinary precision. And when you understand them, even a little bit, you realize that the universe is far stranger and more beautiful than any story about balls moving along paths. This is the real power of physics, as Feynman practiced it. It takes the things you think you understand, the obvious facts of everyday life, and shows you that you've been looking at shadows, approximations, emergent patterns. And underneath those patterns is a reality that's completely alien to your intuitions, but utterly coherent in its own terms. Motion is not real, not in the way you imagine it. But what's actually happening, the quantum fields evolving, the probability amplitudes interfering, the space-time geometry curving, that's real. And it's magnificent. More magnificent than any smooth, continuous journey could ever be. Feynman spent his life trying to get people to see that, to see past the comfortable illusions of everyday experience, to the strange, beautiful machinery underneath. He didn't do it to confuse people or to be difficult. He did it because he believed that understanding the real structure of nature, even when it contradicts your intuitions, even when it makes you uncomfortable, is better than clinging to comforting fictions. So, the next time you watch something move, remember, you're not seeing motion. You're seeing the emergent pattern created by countless quantum interactions averaged over macroscopic scales, filtered through a visual system that evolved to track prey, not to reveal truth. The smoothness is an illusion. The continuity is an approximation. The journey is a story your brain tells itself. What's really there is quantum fields and probability amplitudes and the equations that govern them. And those equations don't describe motion. They describe evolution, transformation, change. Not things moving through space, but patterns shifting in an abstract mathematical space that has far more dimensions than the three you can visualize. That's what Feynman would tell you. Motion is not real. Motion is a useful lie we tell ourselves about reality. A lie that works well enough at human scales, but falls apart under scrutiny. And once you accept that, once you let go of the need for motion to be fundamental, you can start to see what's actually there. Not comfort, not familiarity, truth.